Okay, we're going to look at another example of integrating using inverse trig functions. Um, at first glance, um, this integral doesn't look like it's going to use an inverse trig function, or it fits the pattern necessary to use an inverse trig function. But we're going to do a substitution here, and after a little bit of algebraic manipulation, we're going to see that, in fact, we can use an inverse trig function to integrate this integrand. The substitution I'm going to make here, which is maybe not obvious, is we're going to let u be the square root of x minus 5. We're going to let u be the numerator here in this integrand. And then we're going to go through our usual substitution process, right? So I'm going to take the derivative of u, right? So I can also substitute for dx. So when you take the derivative of u with respect to x, you have to use the power rule to do that. You have to take the u and write it as x minus 5 to the 1/2 power, right? And then apply the power rule. So ultimately, once you go through that process, I'm not going to go through all the steps. You'll get that du dx is 2 over the square root of, 1 over 2 times the square root of x minus 5. So that when you solve for dx in this equation, you'll get dx is 2 times the square root of x minus 5 times du. Now, what we're going to notice here is that square root of x minus 5, right? That was u. And so I'm going to rewrite dx in a little bit different way than I normally would. I'm going to write this as 2u times du, right? Since square root of x minus 5 is u. So that when we substitute for square root of x minus 5 and when we substitute for dx in the original integrand, we're going to come up with u over x plus 2 times dx, which is 2u times du. So we end up with the integral of 2u squared over x plus 2 times du. All right, so obviously we're not quite ready to integrate here, right? Because we still have x in the integrand. So I also have to eliminate this x. To do that now, I'm going to go back to my original substitution where u was square root of x minus 5. And I'm going to square both sides here. Because when I square both sides, notice I get that, I'm going to get that u squared. Let me erase this. I'm going to get that u squared is equal to x minus 5. And so that means that x is u squared plus 5. So I can also here eliminate the x as well. That's kind of maybe the tricky part, or one of the tricky parts of this integral. So I get 2u squared over, so remember that x was u squared plus 5, so I'm going to substitute u squared plus 5 for x, right? Plus the 2 is still there, and then du. So we finally get here, after all of that, 2u squared over u squared plus 7. So I'm still sort of scratching my head a little bit what to do with this integral, right? Okay, it doesn't involve a square root, so maybe it makes it a little bit easier to deal with, but still not really clear at this point how to integrate 2u squared over u squared plus 7. But now I hope you remember at this point that long division can sometimes help us in this situation. Right here we have a rational expression. It's a polynomial divided by a polynomial. This is a second degree polynomial divided by a second degree polynomial. So notice the degree of the top there is at least as large as the degree of the denominator. And so that means that long division may help us in simplifying this integrand or rewriting this integrand so that maybe we can see so that maybe we can see some pattern there that will allow us to apply one of our familiar integration rules, right? So let's try this. Let's take the denominator, u squared plus 7, and let's divide that into the numerator there, which is, of course, 2u squared. So this is not a difficult long division. Won't be many steps. U squared goes into u squared 2 times, right? Okay, and then multiplying back through, we get 2u squared plus 14. And of course, now I'm going to subtract, right? So let's change the signs there and add, and I get a remainder of minus 14. So just one step there in that long division. So that means now I can rewrite my integral here as in the following way. 2u squared over u squared plus 7 is 2, and then minus 14 over u squared plus 7, right? And then, of course, all of this, we're integrating with respect to u, right? Now, I can split that up into two integrals. So I can write this as the integral of 2 du minus the integral of 14 over u squared plus 7 du. And these two integrals now I can actually integrate, right? The first one is very simple. It's very easy to find the antiderivative of 2, right? That's just going to be 2u, of course. And then the second integral, I'll be able to integrate using the arctan function, because notice I can think of this denominator as being the sum of two squares, right? Okay. In fact, let's see, how would we rewrite that? Let's factor out the 14 from the numerator, so I get 1 over u squared, and then we'll write that 7 as the square root of 7 squared, correct? And see, now that fits beautifully into the arctangent rule, right? Here you have u squared plus this constant squared, and so now we know how to find the antiderivative of the second integral. All right, so let's see, what's our final answer here? Let me see if I can squeeze this in. So it's going to be 2 times u, right, minus, let's see, this would be 14 times 1 over square root of 7, because the a here is going to be square root of 7, and then arctangent of u divided by square root of 7. And don't forget here, we need to add on our constant at some point. And now, finally, I have to undo my substitution. So let's see if I have room here to undo the substitution. So we end up here with 2 times u, but remember, u was substituted for square root of x minus 5. That was the original numerator, minus, and then let's see, I can write this as 14 over square root of 7 times the arctangent of u, which is square root of x minus 5 over square root of 7, and then plus the constant. You can actually reduce a little bit 14 divided by the square root of 7, but I'm just going to leave that written as 14 over the square root of 7. So there's our final antiderivative. Well, that's a pretty tough integral problem there, because you have to do an unusual substitution, and then even after you've done the substitution, you have to recognize that you can do long division and then apply the arctangent rule to finish finding the antiderivative.